In this video, we're going to answer a question. If you have a function f over ab, why is it that the average value of that function is defined the way that it is? The definition that we have is given by this integral. The average value of f over the interval ab is defined to be 1 over the length of the interval times the integral from a to b of f of x dx. But why is the average value defined in this way? The more traditional idea of an average comes from summing finitely many things. So suppose we have capital N numbers. Let's write them down. We're already using x for something, so let's use a different letter. Let's say y. So y1, y2, y3, and so on until we get to the last one, which is y sub n. There are n of them. The average of these n numbers is, well, how do we do it? You add them all together, and then you divide by the number of objects that you're adding together, which is n. If we write this in summation notation, it's the sum I goes from 1 to n of y sub I divided by n. This is the more traditional notion of averaging. You can do this when there are finitely many things to add, but if you have infinitely many or uncountably many, that makes it a little bit more difficult. How can you add together infinitely many things? Well, the short answer is that when you have uncountably many things that you want to add together, you use an integral in some way. So it shouldn't be surprising that we have an integral here. But why is it this integral? And why is there a 1 over b minus a there? Well, let's imagine that we don't have a definition for the average value of a function. So suppose we have a function f over ab. And suppose we don't have our definition. So what do we do in order to determine what the average value might be? So we have f over ab, and we want to estimate, that is, estimate the average value of f over ab. So how should we proceed? Let's suppose that we graph it. So this will be our x-axis, and we're going to have some function y equals f of x. F takes on uncountably many values, so we can't use the more traditional approach. But what we can do is we can select a bunch of different x values and evaluate the function at that bunch of different x values and average that. We can get a sampling of values. So even if we're not averaging all of the values, we can average a large sample of values. So let's say that this is a over here, and this is b over here. I want to get a large sampling of x values so that I can put them into f and get a large sampling of f values. I want them to be representative of the values of f. So what I'm going to do is I'm going to choose a bunch of different x values at regular intervals. So I'm going to take this interval from a to b, and I'm going to divide it up into a bunch of smaller intervals. How many intervals am I going to choose? I'm going to choose n. So there are going to be n intervals. So divide AB into n subintervals. Let's make them of equal length. The idea here is we're going to assume that n is really big. we're going to have a lot of values. This formula for computing the average value of a function, or excuse me, this formula for the average value of n numbers works for any n. So what we're going to do is we're going to choose a very large n, because the idea here is that we want to have a lot of different values that, if don't give us all of f, at least give us a good representative of the values that f can take on. So how am I going to do that? Well, I'm going to choose n subintervals. I'm going to take AB and divide it into n subintervals where n is really big. And from each one of these intervals, I'm going to choose a point. I'm going to choose an x. So from each interval, choose an x value. So from the first interval, let's choose x1. So choose x1 from interval 1. Well, this is interval 1 right here, so let's just pick an x1 in there somewhere. Anywhere will do. And then let's choose x2 from interval 2. And here's interval 2, so we'll just pick an x2 from somewhere in that interval. And so on and so forth. So we're going to choose x3 from interval 3. So that's here. And from every interval, so let's say dot, 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 choose x sub I from interval number I, which is somewhere in the middle here. So let's just say that this is the ith interval here. So you're just going to pick an xi. And you keep doing this until you fill in all of the intervals, or until you get a sample from every interval. So choose x sub n from the last interval. So that's the last interval is this one right here. So we're going to choose an x sub n from there. So now we have a sampling of x values, and n can be really big. N could be 1,000, 100,000, a million. N could be really big. And then you'll have so many values for x that when you plug them into f, you'll get a fairly good representative, we hope, of the values of f. So let's compute the average of all of the y values corresponding to these x values. So let y sub I be equal to f at xi for all I starting at 1 and going up to n. So this gives us n output values for the function f. So we have y1 is equal to f at x1, y2 is equal to f at x2, y3 equals f at x3, and so on until you get to the very end. Y sub n equals f at x sub n. Now these y values are just numbers, so these are n numbers. And we know how to compute the average value of n numbers. In fact, we have it right up here. You just add them together and divide by n. So the average of these n numbers is y1 plus y2 plus y3 up to y sub n divided by n. But we know what these are. y1 is f at x1, and then y2 is f at x2, and so on, plus f at x3. Keep adding them together until you get to the last one. And all of this is divided by n. All right, so if we write this in summation notation, this is going to be the sum I equals 1 to n, f xi, and all of this divided by n. Well, let's write this a slightly different way. This is the sum I equals 1 to n f at xi times 1 over n. Let's write it like that. Now, why do I want to write it like that? Let's just go back to our picture. Let's go back to our graph up here. Notice that we've divided our interval into n subintervals of equal length. They're of equal length. That means we can compute the length. So remark, our n subintervals have equal length, and we can compute it. Let's call it delta x, like we usually do. So this length right here is delta x. They're all delta x. Delta x. They're all the same width, the same length. So what is delta x? Well, the whole interval is length b minus a, but we're dividing it into n equal pieces. So delta x is b minus a over n. Or, if you prefer, delta x over b minus a is equal to 1 over n. You might ask, why would you prefer? Well, notice that there's a 1 over n there, and there's a 1 over n there. So what I can do is I can substitute in delta x over b minus a for that 1 over n. So the average value of these n numbers is the sum I equals 1 to n f at xi times 1 over n. But I'm going to replace this with delta x over b minus a. That's going to go in there. So I'm going to have the sum I equals 1 to n f at xi times delta x over b minus a. That b minus a doesn't depend on I, that's a constant. So I can just factor it out. Now, it's in the denominator, so that means it's going to end up being 1 over b minus a in front, times the sum I equals 1 to n f at xi times delta x. And suddenly, this sum should look familiar. This is what we were calling a Riemann sum. What we see here is the average value of the n numbers. Let me just fix that n so it looks a little bit more like an n. But the more numbers we have, the more accurately the average of these n numbers will represent the average of the function. So what we want to do is let capital N go to infinity. This should give us a better representation of the average value of the function. However, as n goes to infinity, we have, well, delta x goes to 0 for 1, but also we have that this Riemann sum, I equals 1 to n of f at xi delta x, goes to an integral, a definite integral, from a to b, f of x dx. So, as n goes to infinity, and our sum, well, when I say sum, I need to be a little bit more careful. What sum do I mean? I mean this. Our average of n values starts to more accurately reflect the average value of the function f. But what is that average value becoming? Well, the average value of the n numbers is 1 over b minus a. It's right here. 1 over b minus a times this Riemann sum. And that goes to 1 over b minus a. As we've just mentioned, this sum here goes to the definite integral from a to b f of x dx. And so this we take to be the average value of f of x over the interval from a to b. And that's why the average value is defined the way that it is.